Namaste, my friend, and welcome back to JEE Chemistry with Typical Monk. This is Class 6, the second step in our bonding journey. Last time, Lewis structures and VSE Pierre gave us the shapes of molecules. But a shape is only a picture. Today we ask the deeper question. Why is methane a flawless tetrahedron? Why does boron trifluoride quietly borrow electrons from fluorine to shorten its own bonds? And why can the carbonate ion never settle on a single structure? For this, we need Valence Bond Theory and its beautiful idea called hybridization, taken all the way to G depth. Sarah once told me she could draw the shapes, but never truly understood them. That changed the day she watched the orbitals themselves mix. Today, one idea at a time, we watch orbitals mix and push a little further than NEET ever does. Take a slow breath. Let us begin. So what will you carry home from today's class? First, Valence Bond Theory and orbital overlap. The idea that a bond is simply two orbitals overlapping and sharing their electrons. Second, the sigma bond and the pi bond. Head-on overlap versus sideways overlap and why one is stronger than the other. Third, hybridization itself, from sp all the way to sp³d², governed by one countable rule, the steric number. Fourth, resonance and bond order. Why carbonate and ozone both refuse to sit still in a single structure. And fifth, the G drills. Assertion and reason. Match the column, counting sigma and pi bonds across whole molecules, and back bonding. So everything you learn today, you can also score with. Ready? One idea at a time. Let us begin with the simplest question of all. What exactly is a bond? Valence Bond Theory gives a lovely answer. A covalent bond forms when two half-filled atomic orbitals, one from each atom, come close and overlap, sharing the two electrons between them. The shared pair now sits in the region between the two nuclei held by both. And here is the key line. The greater the overlap, the stronger the bond. This overlap lowers the energy of the whole system. The two atoms slide together until attraction and repulsion balance, and there they settle, at a fixed bond length, with a fixed bond energy. Valence Bond Theory explains bond direction and strength beautifully, but when David tried to build methane from plain s and p orbitals alone, the angles came out wrong. To fix that, the theory needs one more idea, hybridization. Let us meet it now. Look carefully at this diagram, because it is the heart of today's class. Hybridization is this. The atomic orbitals on the central atom mix together into a set of new, equal orbitals called hybrid orbitals, all of the same energy, pointing exactly at the shape the molecule wants. The first case, sp1 Saha orbital mixes with 1p orbital to give two hybrid orbitals, pointing in opposite directions. That is linear, with a bond angle of 180 degrees, as in beryllium chloride and in carbon dioxide too. Next, sp2 1s mixes with 2p orbitals to give three hybrid orbitals in a flat triangle, that is trigonoplanar, with a bond angle of 120 degrees, as in boron trifluoride. And third, sp3 1s mixes with all 3p orbitals to give four hybrid orbitals pointing to the corners of a tetrahedron, that is tetrahedral, with the famous angle of 109.5 degrees, as in methane. Notice how the number of orbitals mixed always equals the number of hybrids you get. Now that orbitals overlap, let us ask, in how many ways can they overlap? There are two, and G loves to test whether you can tell them apart across an entire molecule, not just one bond. The first is the sigma bond. Here the orbitals overlap head-on, end-to-end, straight along the line joining the two nuclei. This head-on overlap is the largest possible, so the sigma bond is the strongest kind of covalent bond. The second is the pi bond. Here, two parallel p orbitals overlap sideways, forming clouds above and below the bond axis. This sideways overlap is smaller, so the pi bond is weaker than the sigma bond. Now put them together. A single bond is just one sigma bond. A double bond is 1 sigma plus 1 pi. And a triple bond is 1 sigma plus 2 pi. And here is the golden rule that saves you in the exam. The very first bond between any two atoms is always a sigma bond. Pi bonds only ever come on top of an existing sigma. JEE will often ask you to total the sigma and pi bonds across a whole molecule at once. So build the habit of counting bond by bond and adding at the end. Here's a trick that turns hybridization into something you can count in seconds. And then one JEE exception that NEET never asks. The steric number. It equals the number of sigma bonds on the central atom plus the number of lone pairs on it. That single number tells you the hybridization directly, no guessing. Steric number 2 gives sp³ hybridization. Linear, 180 degrees. Think beryllium chloride or the carbon in carbon dioxide. Steric number 3 gives sp², trigonal planar, 120 degrees. Think boron trifluoride or each carbon in ethene. Steric number 4 gives cp³ as in methane. Steric number 5 gives cp³d as in phosphorus pentachloride. And steric number 6 gives cp³d² as in sulfur hexafluoride. And now the JEE twist. In boron trifluoride, boron sits with an empty p orbital and fluorine has a lone pair to spare. Fluorine quietly donates that lone pair into boron's empty orbital. This is called back bonding, and it gives the boron to fluorine bond partial double bond character, shortening it below what plain hybridization alone would predict. Hybridisation pushes this even further. With electron-deficient banana bonds, just a teaser today. The full story waits for p-block group 13. Sometimes, one single structure simply cannot describe a molecule honestly. Carbonate and ozone are the two classic examples, and JEE expects you to know both. Neither ion can be drawn as one fixed structure. In carbonate, the double bond could sit on any one of 3 oxygens. In ozone, it could sit on either side. There is no reason to prefer one arrangement over another. For carbonate, we draw 3 equivalent canonical forms, the double bond shifting to a different oxygen each time, and they merge into one resonance hybrid. All 3 carbon to oxygen bonds equal with a bond order of 1.33. For ozone, only 2 canonical forms are needed. The double bond shifting between the 2 sides, merging into a hybrid where both oxygen to oxygen bonds are equal, with a bond order of 1.5. And in both cases, this spreading out is not just tidy bookkeeping. Delocalization genuinely lowers the energy, so the real hybrid is more stable than any single canonical form could ever be. Now sit up straight. These 5 lines are what JEE actually asks, year after year. 1. Read hybridization, straight from the steric number. Sp is 2, sp² is 3, sp³ is 4, sp³d is 5, and sp³d² is 6. 2. More S character means a shorter bond and a larger bond angle. That is why the angle falls from 180 degrees in sp to 120 in sp² to 109.5 in sp³. Now 3. A sigma bond is stronger than a pi bond, and the very first bond between 2 atoms is always the sigma. A pi bond never stands alone. 4. Total the sigma and pi bonds across a whole molecule. Acetylene, for instance, carries 3 sigma bonds and 2 pi bonds in all, and JEE wants that whole molecule count, not just 1 bond's worth. 5. Back bonding, as in boron trifluoride, and electron-deficient bonding, as in diborane, shorten or reshape bonds beyond what plain hybridization and VCPR would predict. This is the exception layer JEE adds on top of NEET. Let us drill the JEE way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true but the reason does not explain. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion, a bond made from an sp hybrid orbital is shorter than one made from an sp³ orbital. Reason, more s character pulls the shared electrons closer to the nucleus. Check each on its own. Is the assertion true? Yes. Is the reason true? Yes. And it explains the assertion perfectly. Both true. Reason explains. Option A. Second one, assertion, a pi bond is weaker than a sigma bond. Reason: a pi bond is the first bond formed between two atoms. The assertion is true. Pi is indeed weaker. But the reason is false. It is the sigma bond that forms first, never the pi. So assertion true. Reason false. Option C. This is the trap John fell for, mixing up which bond comes first. Third one, assertion. The boron to fluorine bond in boron trifluoride is shorter than a plain single bond would be. Reason: fluorine's lone pair back donates into boron's empty p orbital, adding partial pi character. Both statements are true, and the back donation is exactly why the bond shortens. The reason explains the assertion. Both true. Reason explains. Option A. A quick match now. Say each answer aloud before I reveal it. Beryllium chloride, sp hybridized, and therefore linear. Boron trifluoride, sp2 hybridized, and therefore trigonal-planar. Methane, sp3 hybridized, and therefore tetrahedral. And sulfur hexafluoride, sp³d² hybridized, and therefore octahedral. If all four came to you before the reveal, hybridization is becoming yours. Use a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. Acetylene has 3 sigma bonds and 2 pi bonds in all. Hold your verdict. Statement 2. Benzene has 6 separate, fixed pi bonds, one between each pair of adjacent carbons. Think carefully about delocalization before you answer. Statement 3. An sp hybrid orbital has more s character than an sp3 orbital. So, how many are correct? 2 statements, the first and the third. Acetylene truly totals 3 sigma and 2 pi across the whole molecule, and an sp orbital truly carries 1/2's character against only 1/4 in sp3. But the second one falls. Benzene's pi electrons are delocalized over the whole ring, not locked into 6 separate bonds. That delocalization is exactly why every carbon-to-carbon bond in benzene is identical, with a bond order of 1.5. Now let me save you some marks. 2 myths that trap thousands of students every year. Myth 1. Every bond inside a double or triple bond is a separate sigma bond. It feels natural to just count lines and call them all the same. David believed this for months. But here is the truth. Only the first bond between 2 atoms is a sigma. The extra ones are pi. So a double bond is 1 sigma and 1 pi, and a triple bond is 1 sigma and 2 pi. Never all sigma. Myth 2. In phosphorus pentachloride, all 5 phosphorus to chlorine bonds are identical. The truth, they are not. In this sp3d trigonal bipyramidal shape, the 2 axial bonds standing straight up and down are longer and weaker than the 3 equatorial bonds spread around the middle. That unequal pair is a favorite G catch. Do not let it be the one that costs you. Time to test yourself. Rapid fire. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just what you built today. Question 1. What is the hybridization of carbon in methane? 4 bonds, no lone pairs, steric number 4, sp3. Question 2. How many sigma and pi bonds are in a triple bond? 1 sigma and 2 pi. Question 3. Which hybridization gives the largest bond angle, C, P, C, P2 or sp3? The most S character wins, sp, at 180 degrees. Question 4. What is the hybridization of sulfur in sulfur hexafluoride? 6 bonds, steric number 6. sp³d². And question 5. The thinker. Why is the boron to fluorine bond in boron trifluoride shorter than expected from a plain single bond? Because fluorine back donates a lone pair into boron's empty p orbital, back bonding. If that came to you before the reveal, you have truly understood today's class. Let us gather the whole class in one slow breath. A covalent bond is the overlap of 2 half-filled orbitals, and the more they overlap, the stronger the bond. A sigma bond is head-on and strong, a pi bond is sideways and weaker, and the very first bond is always a sigma. Hybridization follows the steric number, sp sp2, sp3, sp³d and sp³d² for 2 through 6 domains. More S character means a shorter bond and a larger angle, 180 degrees for sp, 120 for sp², 109.5 for sp3. Resonance equalizes bonds and lowers energy. Carbonate at bond order 1.33, ozone at 1.5, and back bonding is the G favorite exception layered on top of it all. And next class, the third and final step of bonding, molecular orbital theory, where electrons belong to the whole molecule, and hydrogen bonding, the gentle force behind water itself. Do not miss it. And so, my friend, we have taken the second step. Lewis structures gave us the shapes, and today hybridization gave us the reason behind them, pushed to the depth G demands. Every tetrahedron, every flat triangle, every linear molecule, and even boron trifluoride's quietly shortened bond. You can now explain, not just memorize. Sarah, David, Lisa, and John all reach the same clarity by watching the orbitals mix, one idea at a time. Be patient with yourself. Tonight, revise just this. Steric number to hybridization. Sigma before pi. Resonance lowers energy. And back bonding bends the rules a little further. Say it once, slowly, and it is yours. One idea at a time, you will card G. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you in molecular orbital theory.